First of all, thanks to the organizers for this opportunity. So in this talk, I will discuss some recent results from numerical side in relativistic spin hydrodynamics. And the talk is based mainly on these two articles. And I acknowledge the support of these agencies during the entire project. Right. Uh, okay. Sorry. Okay, so it was observed a long time ago by Barnett that an initially unmagnetized body becomes magnetized under rotation. And it was observed that the magnetization is proportional to the angular velocity. And this phenomenon is a direct consequence of the conservation of total angular momentum. So the question we ask, can we observe a Barnett-like effect in relativistic heavy ion collisions? And the reason for this question can be understood from this figure. So the idea is two nuclei traveling in opposite directions at ultra-relativistic speeds and at non-zero impact parameter carry a very large initial orbital angular momentum, typically of the order of 10 raised to the power 5. And as the non-participating nucleons break off from the interaction region, they may transfer some of the initial orbital angular momentum to the plasma, causing it to rotate at very high angular velocity. And the quark constituents of the plasma will then polarize due to the spin orbit coupling and, uh, uh, and mimicking Barnett effect. Unfortunately, we cannot observe this directly because the fireball exists for a very short duration. And but we anticipate that the collective rotation of the plasma as well as the quark polarization uh, will leave their imprint on in the spin polarization of final state hadrons. And this has been, such an effect has been um, measured indeed by the STAR collaboration and was reported in the year 2017 as shown in this figure. So the y-axis is the global spin polarization of lambda hyperons, which is directed opposite to the direction of system's angular momentum and is plotted as a function of collision energy, and can be seen the values are non-zero. And the task for the theorist is to understand and explain quantitatively these measurements. So this brings to the purpose of my talk. So I'll discuss in the talk. So there are currently 4 main prescriptions for computing spin polarization. And I will demonstrate with the help of simulation results that if the system temperature is high, is sufficiently high, and it survives long enough, then within the experimental uncertainties, all the 4 prescriptions give equivalent results. So this conclusion is, I've arrived at this conclusion after analyzing the spin polarization data of lambda hyperons in gold-gold collisions at 200 GeV. So before discussing spin polarization measurements, I have to first establish a hydrodynamic stage, which is the background, which on top of which we usually perform all the polarization analysis. So in the next 3 to 4 slides, which may be quite boring, but I'll set up the hydrodynamic stage. So the details of a typical hydrodynamic simulation are summarized in this flow chart. So the simulation begins with an initial condition, preferably with some non-zero initial orbital angular momentum. Then the initial condition is evolved using equations of relativistic hydrodynamics, which are a set of coupled partial differential equations and which have to be closed with the help of an equation of state. Now this evolution is performed until a predefined stopping criterion, which is given by in terms of some energy density. So at the end of this evolution, we have a hypersurface, which is usually in literature known as switching hypersurface. And in the rest of my talk, I will denote this with sigma. Now to compute bulk observables like particle spectra, flow coefficient, particles are usually sampled on this hypersurface. And the sample distribution is then given input to some transport code like URQMD or SMASH. And the output of these transport codes are then analyzed and compared with the data. However, there is another branch which leads to polarization analysis. In principle, this polarization should be computed after the hadronic stage, but unfortunately, in the current setup, none of the transport codes have spin degrees of freedom. So all the polarization analysis is usually done on this hypersurface. So on this slide, I will show the equations of numerical hydrodynamics that we are solving. So this is the equations of conservation of energy momentum and charge. We work in the Landau frame, in which the energy momentum tensor and the charge current take these forms. For simplicity, we'll assume the baryon diffusion to be 0, and the shear stress tensor and the bulk pressure will be treated as dynamical variables, the evolution equations of which have been derived in DNMR framework. So in these equations and in whatever I'll show in my later slides, the dot will denote the co-moving derivative, and this second 4-rank tensor is a projector to project out symmetric, traceless, orthogonal to UMU part of any rank 2 tensor. Now, in this model, I'll just mention the model description. So the initial condition is from Chunshan's group, who have proposed an initial condition model based on global collision geometry, and the longitudinal profile is constrained by local energy momentum conservation. For the equation of state, we have used NUS BQS, which gives a crossover type transition between QGP and hadrons in the entire team UV plane. For the transport coefficients, we use the results from kinetic theory. So I don't have a justification of why we use kinetic theory results, except for the fact that these are the ones which are used in codes like music and VHLLE, and the fact that this works. So the information of the plasma in these coefficients comes in the form of energy density, pressure, and CS square. So we evolve the plasma and then give these from the plasma to these transport coefficients and evolve. The switching hypersurface we will define as the constant energy density hypersurface with the switching value as 0.5 GeV per Fermi cube. And then we have to calibrate our parameters. So these parameters are calibrated by fitting to the experimental data. The results are shown on this slide. So we have, the fitting is done with PT spectra, the pseudo rapidity spectra, elliptic flow for various centralities, and the purpose of this slide to show that the code works fine. Okay, so having set up our hydrodynamic stage, now we go to the spin polarization analysis. So the first and probably the most successful approach till now is based on quantum statistical approach, have been proposed in these articles. And the main quantity of interest is the equilibrium density operator, which is obtained by maximizing entropy, subject to the constraints that the mean or expectation values of the currents match those on the hypersurface. Now, in the Bell-Infante pseudo gauge, where one assumes spin tensor to be 0, the energy momentum tensor is symmetric, and the procedure yields this equilibrium density operator. And right, then after, once we have the density operator, we can compute the mean value or expectation value of any quantum operator by taking the trace with the density operator. And this exercise yields this formula for the spin polarization of spin half particles, and is found to be proportional to thermal vorticity at the leading order. Now, the thermal vorticity is defined here, where beta is known as, it's called 4 temperature. It can be treated as a relativistic generalization of usual vorticity, but it contains much more information than usual vorticity. Anyways, and the mean polarization is obtained by averaging over the hypersurface using this prescription. So to evaluate this expression, we just need temperature, flow velocity, and the gradients on the hypersurface, put in here, compute the integration, and that's it. Now, this exercise has been found to be, and can explain the global polarization measurements very well, as done in this article. And this tells us that the primary driving force for global polarization is thermal vorticity. However, the same exercise leads to a discrepancy if we want to study the momentum dependence of spin polarization, as is demonstrated in this figure. So the right side is the hydrodynamic prediction, which gives a negative sign in the first quadrant, and the left side is the experimental data, which has a positive sign And this problem was termed the spin sign puzzle, but fortunately, this puzzle was not long. Did not last long, because it was soon realized that there is an additional contribution from thermal shear So the polarization has to, which gives roughly the same order of magnitude. I mean, the contribution is of the same order of magnitude as thermal vorticity, but opposite sign. So the net polarization has to be computed by summing the thermal vorticity and the thermal shear contribution. Now, this prescription did improve the results, but the sign was still negative until it was realized that at high energies, the baryon chemical potential at the hypersurface is zero. So the true equilibrium density operator is essentially this, where temperature is outside this integral. And now if one do this exercise for, with this density operator, we have our prescription one for the spin polarization, where this omega and xi are defined like this, and t is a constant unit, is a constant time-like vector in Cartesian coordinates with 1, 0, 0, 0. Right. Around the same time, an alternative approach was, alternative framework was formulated in this article based on gradient expansion of axial Wigner function, and it was applied to axial Wigner function derived from chiral kinetic theory in this article. So the idea is that at the freeze-out surface, if the spin degrees of freedom are in equilibrium, then one should replace this chiral distribution function with local distribution function, Fermi-Dirac distribution, with single particle energy replaced with this, where this delta epsilon is a shift due to spin vorticity coupling. And then once we have the distribution of, once we have an expression for the axial Wigner function, then expand to first order in gradients, and then finally average over the hypersurface, and this leads to prescription 2. So what they observed so there is this mass term here. So what they observed that if we put mass as mass of lambda, then the overall sign, the sign of the longitudinal polarization is still wrong. But if one puts this mass as the mass of constituent quark mass, like 300 MeV, then they get the right sign. And what they proposed is that the memory of strange quark polarization is somehow preserved in the measured lambda spin polarization. And these are the results which I've taken from the original paper. So the top figure is from prescription 1, and then so this is the thermal shear contribution. This is the thermal vorticity contribution, and the net gives a very nice description of the polarization data. Now the bottom figure is with prescription 2. The left is when mass is taken as lambda mass, and we see that the sign is negative. The right one is when mass is the constituent quark mass, and we get a positive sign. But the magnitude is obviously very large than what is observed in the experiments. Yeah, it's true. So they propose that the actual physical scenario is somewhere in between these two. Oh, this. Okay, okay.
I don't think that the point was not the suspicion, but it's a different dependence on the momentum. Sorry, there is a bit transfers. Well, essentially, the fact that there is a speed of u, yeah. So they take a u vector. Yeah, that's, I mean, of course, there is a geometric approximation. Those formulae, there is a geometric approximation. And according to which approximation you take, you have a compressed geometry model.
Okay, so this is fine, and now I'll go to an alternative formulation, alternative approach to spin polarization, and the main, which is based on relativistic spin hydrodynamics. And the motivation, as far as I understand, is that the prescriptions 1 and 2 assume instantaneous equilibration of spin degrees of freedom. And there are studies based on microscopics that suggest that spin relaxation time is comparable to the lifetime of the fireball. And then this is a suggestion that spin dynamics cannot be neglected. And the relevant equations for spin dynamics must be derived from the equations of conservation of total angular momentum. So the idea is that if one works in a pseudo gauge where spin tensor is not zero, and then one can separate the total angular momentum into an orbital part and a spin part, And the orbital part is this. So when we substitute in this equation, the equation for conservation of total angular momentum, we get an evolution equation for the spin tensor, where the right-hand side is the antisymmetric part of energy momentum tensor. However, this procedure has a fundamental problem in the sense uh, that the energy momentum and spin tensors are not uniquely defined. There are infinitely many choices of uh, spin tensors and energy momentum tensor that give the same equations of motions and the same set of conserved charges. So there is this fundamental problem, and there is no general consensus. There is no general consensus on what is the, how to choose the physically relevant pseudo gauge. But as far as I understand, which may be wrong, that if one adopts a microscopic approach such as kinetic theory, and then derive spin hydrodynamics from kinetic theory, then one can work in any pseudo gauge. And the result, and if everything is done consistently, then the result should be independent of pseudo gauge. So I'm not an expert in this theory, but I assume this philosophy to be correct and proceed further to see what they have to offer. So the first approach, the kinetic. I'm talking about local equilibrium. Sorry. Yeah, local equilibrium. Sorry, what is the question? I mean local equilibrium. Sorry. I'm sorry. So this means local equilibrium. I'm talking everything in terms of local equilibrium. I don't know if I've answered your question. Okay, so in the yeah, I mean, if you so I'm going to show it towards the end here. So now again in the kinetic approach there are two versions. Version proposed in this article, where they formulate the Boltzmann equation in an extended phase space with local collisions only. And then in this particular pseudo gauge, the known as GLW pseudo gauge, they obtain a symmetric energy momentum tensor, due to which the spin tensor satisfies a conservative equation, means that total spin is conserved. Now, in the approximation or in the limit of small polarization limit and in local equilibrium, they get this structure for the spin tensor, where this omega is called spin potential, and kappa is defined like this. And A1, A2, A3 are some coefficients dependent on mass, temperature, and chemical potential. Assuming Boltzmann statistics, these are the analytic expressions for these coefficients, and which I will use for my numerical simulations. Now, in the so a simplification occurs in the small polarization limit, that spin evolution decouples from the background. That means, I can solve these equations independently on top of a hydrodynamic background. I just need information of temperature, chemical potential from the background. So we solve. So the task is to solve these equations, and there are algorithms available that particularly deal with conservative systems. We have adopted a scheme based on finite volume method. So I'll just outline the idea. I'll not go into the details. So the idea is to discretize the domain into fluid cells, and then replace the function with a constant cell average. After this procedure, at each cell interface, we have a left constant state and a right constant state, and we get a Riemann problem. Now, one can solve this Riemann problem exactly or approximately, but exact solution requires are computationally expensive. So we've solved these Riemann problems using an approximate Riemann solver, which is based on relativistic HLLE prescription. So having solved Riemann problems at each cell interface, we then know what is the flux that enters or leaves a particular cell. So in this way, we compute the net flux that leaves a cell and update the cell values accordingly. I like to only mention that this scheme is conservative, and we have checked that the loss in total spin is about 3 to 6%, and this is, in principle, it should be even smaller, but I've not been able to. So this range depends on the choice of the transport coefficients in the background. So since there is a loss in the background, it somehow propagates into the spin equations, and we have this much loss. So we implement this scheme in a new spin hydrodynamic code in this article. And right, so we have a spin hydro equation, and then we want to solve it. But to solve these such equations, just like similar to traditional hydrodynamics, we need an initial condition. And I'll also like to point out that in this approach, they have assumed local equilibrium. They don't have an explicit relaxation mechanism. So the initial time has to be treated as a parameter, similar to the traditional hydrodynamics. So in total, there are now two parameters in this approach, the mass of the particles and the initial spin time. For the initial condition, we use this prescription, which is motivated by the equilibrium approaches. So the first part is the isothermal part of thermal vorticity. And this is the isothermal part of thermal shear. What I mean by isothermal part is I simply ignore the gradient contribution to thermal vorticity. And this tau is a unit vector normal to constant tau hypersurface, because we want to initialize our spin hydro on a constant time hypersurface. And then with this prescription, we evolve our spin hydro and extract the spin potential on the switching hypersurface and calculate the spin polarization using prescription 3. Now, this has also been derived by Matteo in this article in the GLW pseudo gates. So in that sense, we are consistent. Now, time for results. So as I said, so there are two parameters in this approach, the mass of particles and the initial spin time. So we first fix mass of particles to be lambda mass, and then plot the spin polarization for different values of initial time. Now, these numbers should be compared with the initial time of hydrodynamic background, which we take to be 1 Fermi. So the left figure is the y component of polarization, and the right figure is the longitudinal polarization. So what we observe from here is that, so if we assume this local equilibrium and start at the same time as hydrodynamic background, then the polarization will be too large. So to get a correct description of the data, one should take a delayed, the spin sector must evolve at a delayed time than the background hydro. So we found that a good fit is observed when the initial spin time is about 4 Fermi. And these results suggest that, so the question is what happens between 1 and 4 Fermi. So since in this approach there is no relaxation mechanism, so this is just suggestive of the fact that between 1 and 4 Fermi, the spin actually relaxed to local equilibrium. And after that, it becomes a conservative process. Now in the next figure, we fix the initial spin time and vary the mass parameters. So the left figure is when mass is 300 MeV. The right figure is when mass is the lambda mass. And we compare our results with prescription 1, which is the blue dashed line, and prescription 2, which is the dotted line. And these are the results. So what the results? So as you can see, a good fit is observed for a smaller value of mass, which is indicative of the fact that relaxation is faster for less massive particles. Now this brings me to to another approach which has been proposed in this article, and of course there are many articles before this. But the main idea is that you start with a Boltzmann equation, but the collision term has an additional contribution from non-local collisions. Now, the inclusion of this non-local collisions provide a microscopic mechanism for the transfer between spin orbital angular momentum and orbital angular momentum, as is depicted in this figure, which is slightly misleading, but gives the essential idea. So when suppose we consider two spins which are in the up stage, if there is a separation between them, then you have a non-zero orbital angular momentum, and this may lead to a spin flip process. I mean, so this microscopic approach essentially facilitates, the non-local collisions essentially facilitates spin equilibration. Am I right? Okay. Now, to do any computations, one has to first define local equilibrium. So in this formulation, the local equilibrium is defined as this. So the distribution which makes the local part of the collision go zero. But it has to be, it should be noted that this condition does not mean that the collision term is zero, because you have this we have this non-local contribution, which may not be zero for, which may not be zero for this distribution. Now, due to this, what happens that even in non-equilibrium, even in local equilibrium, one has an antisymmetric contribution to energy momentum tensor because of non-local collisions. So, so the ideal spin hydrodynamics, which is defined as the one when the distribution is in local equilibrium, one can derive the equations. So one can take the moments of the Boltzmann equation and integrate over the phase space to arrive at these equations, which are the ideal spin hydrodynamics. Now, there are two key observations. So first, the spin is a quantum effect, which is h bar, which is of the order of h bar, which is different than the approach I discussed earlier, where they treat spin as a leading order term in this h bar expansion. The second observation is that there is no back reaction of spin on hydrodynamics. So this is again, so we can solve spin hydro on top of the background in an independent way. Okay, so this was the case when it was in local, so the distribution was in local equilibrium, but it's not very interesting. So the interesting thing is when you deviate from local distribution, and this will lead to dissipative spin hydrodynamics. And the dissipative spin hydrodynamics have been derived by David in this article. It's a very detailed paper using moment expansion method. I only have a few comments here. So the moment equations themselves are pseudo-gauge independent. The pseudo-gauge dependence only comes when one tries to derive spin hydrodynamics from these moment equations after truncating and in form of matching conditions. But as I mentioned earlier, that if everything is done consistently, then so for example, if one works in a different pseudo-gauge, one will get different transport coefficients or different equations that have to be solved. But the final outcome should be independent. So it should be independent of this choice. Sorry, am I clear what I want to say? Okay, so now, so if one derives the equation of spin hydrodynamics from this moment equation, it is natural. So the equations come out. Okay, sorry. So in this method of deriving spin hydrodynamics, the natural variables for spin evolution are not the spin tensor, but omega, kappa, and t, where omega, kappa are defined like appears in the decomposition of the spin potential. So this omega is the magnetic part of the spin potential, and kappa is the electric part of spin potential. And this T is, we call it spin shear stress, which shares the same symmetries as as pi, which is shear stress tensor. So it's a rank 2 symmetric tensor, traceless, and orthogonal to U mu. And it has a dissipative effect as it controls the evolution of spin potential in the similar way that the pi, the shear stress, controls the evolution of flow velocity. And in the context of spin polarization, it will we will see that this plays a role which is similar to thermal shear in the equilibrium approach. So the equations derived by David and that we solve numerically are shown here. So I don't have a, I mean, of course, so the first terms on the right-hand side are the Navier-Stokes limits to which the quantities approach in the long time limit. So this omega kappa is essentially defined. So various terms which appear here are defined at the bottom. So this omega kappa beta is the magnetic part of kinematic vorticity. U dot mu is the electric part of kinematic vorticity, and then there are a bunch of transport coefficients. The relaxation to their Navier-Stokes limit are decided by these time scales, tau omega, tau kappa, tau t. And yes, so the task is we want to solve this numerically. Now it turns out that all these equations can be cast into this form, and which is the exactly same form as the viscous hydrodynamics, I mean the pi and capital pi, and is a relaxation advection equation. So, and for which the algorithms exist in the literature. So what we do, we split this equation into two parts using strength splitting method. So the first part is the relaxation equation with a source term, and the second equation is the advection equation. So to solve this equation, we use the piecewise exact solution method, which says that if the time step is greater than the relaxation time, then you update the solution according to this. And if the time step is less than the relaxation time, then we approximate. So this equation can be solved exactly. So we use the exact part, and this is treated as a correction. Now, once we have an updated solution, we can put it in the advection equation and let it evolve using a upwind scheme. Now, it is to be noted that this step is done twice. So this is a second order accurate method, as can be seen, because we have n plus half, which means we store the information at half time step 2. Okay, so now the only information that we need to solve these equations are the transport coefficients. Now it's not possible to discuss all the transport coefficients here. So I'll show two, which I feel to be most important. So one is tau omega, which is the longest time scale in the system. And one is this transport coefficient D, which essentially determines how large is your dissipative, uh, so how large is dissipation in the system. So so these coefficients are computed for 3 interactions. So this green line is for a scalar interaction. The red line is for a scalar pseudo-scalar interaction, and the blue line is for a vector interaction. Now it turns out that, so we have this coupling constant, and it turns out that the transport coefficients, they are independent of G if computed in terms of ratios. So for example, if I compute tau omega and tau pi, G does not matter. What matters is the nature of interaction. I mean, okay. So, yes. Oh, sorry, I forgot. Yeah. So G is m by t. Yes. This one. Yeah. So this is the transport coefficient appearing here. So the spin shear stress in the infinite time limit approaches shear stress by temperature with this transport coefficient multiplied. Sorry, sir. Yes, yes, D is dimension. Yeah. So this is a dimension of GV4. Yes. Are you talking about this plot? Um, no, but she's so this is the so is Z is 1 by temperature actually. M by T. So yeah. So when temperature is large, you are going in this limit, right?
Yeah, but then if you take some reasonable values for M and T, yes, then you get a tau omega with tau pi, you know, essentially one, even less than one. Yeah. So that means that the relaxation doesn't mean the relaxation time of the scale essentially the same order. I would say that it is faster because the ratio is less than one. It's 0.9. If I take M over T equals 1. The red curve. The red curve, yeah. Ah, right. Ah, because you have a depends on the interaction. You favor the x one. Yeah, depends on the interaction. Yeah.
So okay. And okay. Okay. So we have now these three interactions, and please remember this color code because this will be used later. So this red will stand for scalar and pseudoscalar contribution. The green one is just scalar, and this is the vector contribution. So now to analyze our spin polarization data, so we will be analyzing the data in 20 to 50% centrality, for which we have checked that the mean impact parameter is 8.4 Fermi. And so with this impact parameter, if we evolve the system, then the Z, I mean, if I define a mean temperature, then the mean Z is essentially in this range, 1.2 to 1.9. So that means in this range, the ISP interaction has the lowest tau omega, and then these are almost comparable. However, the dissipative correction for the vector interaction, we have, I mean, in this range, the vectoric interaction has largest D, then scalar, and then, then pseudoscalar, and then scalar. Okay. And then this is the prescription 4 for computing spin polarization. So we have a contribution from omega, a contribution from kappa, and a dissipative contribution. So it is to be noted that if there are no local collisions, then the omega and kappa is essentially, so this two together is essentially prescription 3. But now, since there is a mechanism for spin equilibration, and so we have this dissipative correction, which is given by this. So, right, so this is our prescription 4 to compute the polarization, spin polarization analysis. And I think I don't have anything else to add, except to say that, yeah, so these two are equilibrium, I mean, it's like spin potential, which is prescription 3, and it's a dissipative contribution. Sorry. Except for this turns coefficient, this is actually thermal shear, right? Yes, yes. So in the infinite time limit, this actually approaches the one which has been, which is prescription 1, the equilibrium approach. But this is dissipative. So we have an additional contribution to and now, okay, so after all these details, now we solve this spin hydro on top of hydrodynamic background. We take the information of temperature, flow velocity, gradients, and solve these equations by fixing the mass to be the constituent quark mass, and assuming that the form of the transport coefficients, it's same for the plasma. The only information of the plasma comes in form of tau pi and pressure. So we give this information to spin hydro and let it evolve. And these are the results. So the left-hand side is the spin potential. So, okay, so first of all, we have chosen an initial condition model where, due to symmetry, the only xz component of spin potential is non-zero. The rest are 0. Okay, sorry. Okay, let me first define mean value which we want to plot, which is a space integration of energy weighted quantity, because this is the only quantity which we could think of to extract as much information about the spin evolution as possible. So with this definition, we have, so due to symmetry, due to symmetry of the initial condition, when we do this integration, almost all of the other components of spin potential will be 0 except for the xz component. Now this dotted line, the black line, is thermal vorticity. And to get rid of any uncertainty associated with the initial condition, we initialize omega, kappa, t, everything to 0. So this is our initial condition. And so what we see, so initially the system is far from equilibrium, but then due to different relaxation mechanism, it approaches thermal vorticity. And then now, if you remember the plot of tau omega, the relaxation is faster for the red curve, which is our SP, pseudo-scalar interaction. And then we have this scalar and vector interaction. And then we see that within the lifetime of the fireball, everything approaches the thermal vorticity. Now, regarding this vector interaction, we initially thought this to be a numerical problem, but we checked, confirmed, we did some numerical experiments, and what we found that this is actually a physical effect. There is an overdamping due to vector interaction because the tau kappa, I mean the relaxation time of the electric part of spin potential is very large. So what happens? So there are competing, so there is a competition between this term and this term. So this term has a dissipative effect, whereas this tries to relax the kappa to its corresponding Navier-Stokes limit. So initially this is dominant, which leads to a damping, but after some time, the relaxation dominates and drives it towards equilibrium. And on the right plot, we show the time evolution of the mean of ZZ component of T. There are other components, but this is the most dominant contribution here. And what we see that initially the dissipative, it quickly relaxes to its Navier-Stokes limit, which is this. So at very large time, this effect is essentially zero, but and this is this is easily understood because we are now closer to the equilibrium. Okay, so next we now we evolve the spin hydro and then extract spin potential. So we extract omega, kappa, T at the switching hypersurface, and then we set out to study the effect on individual contributions to spin polarization. So the left plot is the Y component of polarization. This is the omega contribution, kappa contribution, and T contribution. This is the longitudinal polarization. So the two interesting features. So first, the dissipative contribution to spin to Y component of polarization becomes large at large PT. So initially at low PT, this is zero. Which is expected from kinetic theory that at low temperature, low momentum modes are closer to equilibrium. But this dissipative contribution actually becomes large at high PT. Another interesting feature is that the dissipative contribution to longitudinal polarization is sensitive to interaction. And the rest of the features, like for example, this, the omega contribution to the longitudinal polarization is very small, which is in agreement with the equilibrium approach. And then the kappa is essentially, okay, so the acceleration part. That is not true because the freeze out information is from all time, right? Yeah. So it is just omega converges to the two theory. Okay. Yeah. So besides this ID, right? Well, then we have the Stokes, the pseudo-scalar and scalar interaction. Right. Two Fermi, essentially, the spin potential is locked to non-vorticity. So unavoidably, you will find the same results as for the first two terms. If you show that your spin formula, this one, yes, yeah. Yes. So you have this is this omega is, but omega is just the vorticity part, right? No, this is, so these two should be thermal vorticity, yes. These two together. One is magnetic, yes. Yeah. So they essentially will be the same formula as the thermal vorticity in the local equilibrium. Yeah, but then this implicitly includes all the temperature gradients. So if we go to these equations, they look complicated, but in the infinite time limit, of course, we get the same limit as the equilibrium approach, but in principle, it is not because we have contributions from all these terms. So the temperature gradients are actually included implicitly there. Am I clear? So after adding these three, we still have temperature gradients hidden inside. Temperature gradients as well, yes. Yes. Right. Okay. No, I cannot see the difference. So once you show that the spin potential converges to the voltage, so the question is whether you have a difference in this. So
First two compared to the
no, so okay, so okay, I don't know how to. Okay, so this is not the freeze-out hypersurface.
I agree.
So the freeze-out the contribution has to be integrated over all the times.
This is tau. This is tau. This is the Bjorken tau, right?
Yes, this is Bjorkanta, right?
So the hypersurface, the freeze-out hypersurface, more or less.
Mhm.
Okay, for the large part, it's tau equals one. Tau equals one. Okay, it's a hyperbole. It's a hyperbole, right? More or less.
Fraction of particles, if you say it's true. The fraction of particles can be 0.4 close.
Yeah.
Let's say even less. Like we say, like
Yeah. Okay. Yeah.
80% of particles particles. Like
Yeah. More or less.
more or less.
Okay.
So we should be looking only the last point on that curve. Where it's dominated, it's just the last one.
I'm not sure this comparison is entirely correct because the two approaches are, I mean, totally different, right? So if I consider prescription one, they don't have any temperature gradients in the formula, right? If I correctly understand. But even this 20%, as I will argue,
You're saying that, oh, but skin dominated by power two. That's very important and worrisome because it's all the identifiers as opposed to the part that we trusted. That's how
okay.
The other question following. So you have also this Gothic TZZ, right?
Yes.
Yeah. So how does this compare to the shear?
Yeah, so you can see, so
Does it converge to the shear then? Yeah, no.
this, but with,
Do you have a similar plot that you showed?
yes, I'll show that.
You
Sure.
can show the spin potential and then a curve with a number of these.
Yes, I'll show that the next slides. Okay, so the main takeaway message from this figure is the dissipative correction gets larger at high PT for Y component of polarization, and the dissipative correction is sensitive to the type of interaction considered in the considered to derive the transport coefficients. And okay, so the net polarization has to be obtained by adding these contributions, and this we do here, and this is plotted here. So these are the experimental data points, and these are for 3 different interactions. So what we see that within the experimental uncertainties, the Y component of polarization is not sensitive to the interaction. However, the longitudinal polarization is very sensitive to the type of interaction considered in the system. And now this is the comparison with prescription 1. But now one has to be very careful because we are using an equation of state which has non-zero mu b. So the isothermal approximation is not exactly valid at the hypersurface because mu b by T ratio is approximately 0.2 at the hypersurface. So what we do to make this plot is to simply, so we consider 2 cases. Once we include the temperature gradients, and once we simply drop off the temperature gradients. So this omega bar and xi means temperature gradients are present. The ISO means we have simply discarded the gradient, temperature gradient terms. So what we see from here, for the longitudinal polarization, if we include the gradient part, the longitudinal polarization is negative. If we simply assume the isothermal approximation and discard the gradient terms, then we get a positive sign of the isothermal, positive sign for the longitudinal polarization. And this red curve is one which includes everything. Temperature gradients, right? There's no approximation. The only approximation is the mass of the particles is 300 MeV, and the type of interaction is SP. scalar pseudo-scalar. So now this is the comparison. So what is the question? No, I mean, you wanted to, so this is the comparison which you asked for.
PCC past the shear sequence or to phi or to the thermal.
Oh, sorry, I don't have a plot here, but okay, so if I plot sigma mu nu by T, then you will see something like this. So it starts from very large value and then it approaches this curve.
Okay, so that's the same. So which means that it's basically the same feature as for this.
Yeah, sure. So it converges to the asymptotic. Yes. Yes.
So that means that eventually those form.
No, but then we have this D term. Sorry. Yep. Which controls the magnitude of the shear term.
But how? But is D calculated or fitted?
No, D is calculated. So this is D. Sorry. Yes. So I have the plot. I mean, I don't have here, but it's shorter. Yes, it's shorter. So this is the largest time scale in the system. So that's why I had this. Yeah, tau kappa and tau omega are almost comparable for these two interactions.
So eventually, what is the difference?
So we have a dissipative contribution here.
Besides the fact that, as far as I understand, it's not clear whether this is dissipative or not.
No, so so the local equilibrium is this, and any deviation from this distribution is non-equilibrium.
This is
Yes.
okay. So but if you then sum up all of them, right, and then you get similar. So if you look at the comparison with the data,
This
you have,
one.
yeah,
Yes. Right.
you have this the isothermal freeze-out method. Then you have fair agreement with the data. Well, let's forget about the data. So you have
Okay.
forget about the data. So you have a comparing. Let us compare the blue line with the red line.
Okay.
Okay, the blue line and red line almost the same.
Okay, I can do a better job in. No, I can do a.
This result is linked to the fact that if you sum all those terms, you get essentially the same formula as for the total equilibrium. With the same coefficient, exactly. So what's the difference?
I have not done this calculation, so I don't know.
Okay, so this seems to be accidental because if I understand that the break is accidental because in the kinetic formula, let's say you don't have a T vector, you have a U, or then you have this D, which is calculated, and then you have also thermal gradients are included, and then you get something like that. The thermal gradients don't appear because they don't appear as well. But this is something to result. So if you don't have the thermal shear, okay, good. They don't appear in the formula. Okay. What is the 1 over
Sorry, can you repeat the question? Yes.
And then take this thing and you just multiply by some moments to find equations for T mu and omega. What is that?
No, that is not true. That is true for ideal spin hydrodynamics, but if one has to do away from equilibrium, then one has to write moments equation. So there will be a infinite series of moments. Then you have to do some truncation and some matching conditions, and then derive the equation. Yes.
The equation doesn't.
Yes, sorry.
Relaxation of the field tensor has this right hand side. Antisymmetry might have been removed. That has the number. So the omega and kappa relaxation of the field tensor. This thin shear becomes from the double moment of the bottom.
Okay, so right. Yeah, okay. So of course, all theories cannot be perfect. So there's a problem here. So we have this mass parameter in question, and then we studied the sensitivity to mass parameter, and the results are shown here. So within the experimental error bars, I would say the Y component of polarization is not very sensitive to mass. However, the Z longitudinal polarization is very sensitive to mass. So if we take mass to be 100 MeV, we get a wrong sign of the polarization. Really positive. Really positive. Positive. So 300 MeV, 500 MeV. E- I I know I have to check, but yeah. Yeah, so there's a mass of the spin particles that are being evolved on top of the background.
But if you look at, if you go to the formula, so again, this, we have m lambda.
Oh, sorry. So this is m lambda. Sorry. So this is m lambda. But for the evolution, we need to compute this transport coefficients. So we have to put this mass. So these are the mass of effective mass of particles that are evolved on top of the background. Yeah. So this is sorry. I mean, okay. So this mass is lambda mass, but this mass parameter is the effective mass of quarks, which are being evolved on top of the background, and they go into the computation of this transport coefficient. Yeah, so they decide the transport coefficients. So what I mean to say, so the main message I want to, I think, yeah, so the main message I want to convey from this figure is that dissipative effects are necessary in the kinetic approach to describe the polarization measurements. So with this, I come to the summary. So so most of the studies based is guided by the polarization measurements and, sorry. So I've presented 4 prescriptions for spin polarization computation. Okay, so my analysis is done. So the analysis is done for polarization measurements from gold-gold collisions and 200 GeV. And as we go to this figure, we see that everything actually converges to thermal vorticity. So in this respect, all the 4 prescriptions are equivalent. However, when we go to lower collision energies, the lifetime may not be sufficient for these to go to the equilibrium values. And then the real test of these formalisms, the real test of these prescriptions will be when they are applied to lower collision energies or small systems. But at this moment, I don't know, all are equivalent for 200 GeV. So yes, so thank you.
Is there a calculation of why it's less than one or more than one, just to see how the different
What is less and what is more? Mass. This figure? Is this the one you're talking about?
It's the part I'm talking about. I mean, here in all of these, it's more than, it's basically more than one. Is there a calculation where it's sort of considerably less?
Just also is not fast as opposed to everybody is the most much basically the next plug you can see that process is just
Yeah.
yeah, here. What is first go faster which you're talking about. Yeah. So I want to expand your computing. That all these approaches give a real result. So now, okay, such a claim tries for analysis of how many few parameters you have put in order to reproduce the data. And as far as I understand, that in the prescription number 3,
Yes.
you have to adjust this tau, not
Yes.
in a way to reproduce the data.
Yeah, that is because they don't have a relaxation mechanism, but they're working on it. And as far as I understand,
Okay, so, prescription 1 and 2 is a straightforward prediction. Okay, so there is a formula which is, does not require any additional pre-parameter, and either you get the data, you don't. Okay, and in fact, this was in this case. I think in the third, at least the prescription number 3,
yeah.
you have one more parameter to adjust, right?
Yeah, but if we go to this plot again, this one.
No, prescription number 3.
No, no,
Not 4. 3.
no, no. So what I want to say, sorry.
Prescription 3, not 3.
Yeah. So what I want to say that prescription. No, no. Let it. So what I want to say, the prescription 3 and 4 are essentially same after this time step, right? So as you, if you remember, no,
You have tau 0, yes.
Yes.
I'm going to show the plot.
Yes.
Yeah, right, exactly.
Yes. Now, what I want to say, so this tau spin, I mean, if you remember this 4 for me, is essentially this almost same as here, right? So what I want to say is that in the beginning, in the initial evolution, the spin, so this dissipative effects play a very important role. But after that, you can see, I mean, they're essentially same. So spin conserving processes dominate. So if I'm applying prescription 3 after this time step, is fine. I mean, there's no problem.
See that you have one more parameter. In order to fit the data, you have to vary it, otherwise you don't get it. This is, I mean, very, very simple.
Prescription 3 has a little constraint that you don't have a dissipative effect due to normal.
Okay, so so if I go to if I go to this equation, now if I write this T nu mu is essentially omega minus omega bar. So that means the difference, this essentially is the difference between the thermal vorticity and the spin potential. So what I want to say from prescription 3, that if this difference is small, which is now clear from this approach, T mu is essentially, antisymmetric contribution is essentially 0. Yes, I mean, of course. Yeah. Yeah, sure. I agree. Yeah.
Okay, so you have to choose one more initial. In this case, you have the prescription that you can take spin potential, which is 0.
Yes.
Right.
Right. Right.
Okay, which is somehow it is it's not a fit. Just to constrain this to be.
Sure.
But I mean, in the case of prescription 3, I would like to make a general comment here. So, regardless of how the problem is being solved, or try to solve the problem, it seems to me that one of the crucial ingredients is local equilibrium. So, how to define local equilibrium? Because that is for the fact that the spin potential in the quantum theoretical approach, that the spin potential and the spin tensor, okay, modify the local equilibrium density variable in such a way that you have dependence on the spin potential and so on, right? And this is precisely what Numerical calculated. The formula of the spin potential, which is proportional to the spin polarization to the spin potential, entirely depends on the choice of the local equilibrium density variable. Okay, and similarly here in the kinetic calculation, the local equilibrium distribution function plays a major role.
No, I agree, but I'm not an expert in these calculations. I just code, so these issues, yeah. But in my understanding, so if I go to this, if I use this equilibrium approach, you match this expectation value to T mu, right? But I've never seen expression which involves the dissipative part of T mu. I understand that these calculations are difficult, but shouldn't that also be a contribution to the spin polarization formula?
This is something that it's a subject of discussion because you know that the relativistic kinetic theory, what you call dissipative, corresponds in form, have some digits perhaps, but it corresponds in form to what is